Hello everyone. Now today we will see the next topic from this curves and fractals, that is Hilbert curve and the Koch curve. Up till now we have seen the what is the curve, then which are different methods for the curve generation. After that we have seen the two types of curves, that is B-spline and Bezier curve, and then we have seen in the last video that is fractals. What is the fractals and which are the different dimensions used for the fractals. So this Hilbert curve and this Koch curve comes under the fractals. What is the fractal? Fractal is nothing but one formula we are repeating again and again with the slight variation of their parameters or values, and the fractals are nothing but complex pictures that are generated from a single formula that can be used repetitively to form a curve, that is called as a fractals. Now we'll see the type of fractal. The first is Hilbert curve. The fractal dimensions are shown by the DF, and we are calculating the fractal dimensions for each curve. Now we'll see what is Hilbert curve. The question on that Hilbert curve can be like write a short note on the Hilbert curve, or explain the Hilbert curve with an example. So this is again a very important topic, and we have the assignment on this Hilbert curve and Koch curve in our practical. So these are the two assignments which we are going to cover in our CGL practical. Now we'll see what is Hilbert curve. So to generate this curve, before that we'll see what is the shape of this curve exactly. So it is also called as a piano curve. So it look like a keys of piano. Then it is very easy to implement, and this curve is start with a square. So initially we have a square. This square is divided into the 4 different quadrants. So initially we are having a square, we are dividing that square into the 4 quadrants. So the generation of the curves require the approximation, successive approximation. So what is the first step? The first approximation, that we are dividing the square into the 4 quadrants, and then we are finding the center of that each quadrant. So here we are finding the center of each quadrant. Then what is the next step? Then we have to connect this center point of each quadrant by the line segment. So we can see here, this is what the square. Then we are finding find out the center points of that each quadrant. After dividing that square into the quadrants, we are finding the center points, and then we are joining that center points by line segment. So this is what the first approximation of this Hilbert curve. Then what is the next step we have to do? Again we are going to divide that each quadrant into 4 quadrant, means we are making the subdivision of each divided quadrant into 4 subdivision of quadrant. So you can see here, this main 4 quadrants are again get divided into the 4 different sub quadrants. So again you are finding the center of each sub quadrant, and then you are joining the line of that each center of each sub quadrant. So the curve will look like this. So this is called as a second approximation. What you are going to do in the next approximation? Again you will divide each quadrant into the 4 quadrant. Again you have to divide each of this quadrant into 4 quadrant. Again find out the centers. Likewise this process will goes infinitely long. Okay, this process will goes infinitely long for drawing this Hilbert curve. So we'll see one by one. So it is also called as a piano curve. It is very easy to implement. It begins initially with the square and requires a successive approximation. So what is in the first approximation? The square is divided into the 4 quadrants. Then we draw the curve. How we are drawing the curve? By connecting the center point of each quadrant. This is called as a first approximation, shown like this. Then what is the second approximation? Again we subdivide each 4 quadrant into the sub quadrant. Then we are drawing the curve again by connecting the center point of each subdivided quadrant. This is called as a second approximation. Then again what we are going to do? Again we are subdividing the each quadrant and will process continue. We'll process this continually. Now you can see here the curve fills the square, means whatever the space is there, this curve is filling that all space by square. Okay, and ideally its length will be infinitely, because this is the infinite process. If we are not stopping this, it will going continuously. So this is having the length ideally as a infinity. Okay, so these are nothing but the approximation, the diagram showing the first approximation and second approximation. So how to draw this line? So you have to starting from this point, drawing this curve like from this point to this point. So we are moving from this quadrant to this, after that this quadrant, and then the next quadrant. So in this way the line will be filling the square. So this is how the Hilbert curve is drawn. Now we'll find out what is its dimension. So as we all of you know that this curve is made up of only the line segments, so we can say that its topological dimensions will be 1. So we can easily say its topological dimension is nothing but 1. And with each subdivision the length is increases by the factor of 4. Whenever we are dividing, the length of a line will be increasing by the factor of 4. Its topological dimension is nothing but 1. And whenever we are dividing the each quadrant into 4 quadrant, at that time the subdivision scale is changing by 2. That means we are making the half of each quadrant every time. So the scaling factor is nothing but 1 by s is equal to 1 by 2. Therefore value of s is what? The value of s is nothing but 2. We are making its half always. And what is the length of the curve? For each subdivision of quadrant, the length of curve is 4 times of its previous curve. So it is increasing by the factor of 4. So we have the formula that we have seen in the last lecture, that is n is equal to s raised to df. N is nothing but the number of subdivision we are making, and s is nothing but the scaling factor by which we are scaling that object. So that n is nothing but s raised to df, and df is nothing but the fractal dimension. So we have to find out the fractal dimension of this Hilbert curve. So we have the formula that n is equal to s raised to df. N is what? The number of subdivisions. So we are saying that for each subdivision of quadrant the line is increased by factor of 4. So it makes the 4 different lines whenever we are subdividing into the quadrants. Therefore n is equal to 4, because line is divided into the 4 parts, and s is nothing but what is the change? So scaling factor. Scaling factor is 2. We have seen that we are making the quadrant half every time, so scaling factor is 2. So how we get the df? So 4 is nothing but 2 raised to df. So we can say that 2 raised to 2 is nothing but 4. So value of df is nothing but 2. df is nothing but, that is fractal dimension. So this fractal dimension of Hilbert curve is nothing but 2. So topological dimension is 1 because it is made up of line segment, and the fractal dimension is nothing but 2 because we are finding with that formula n is equal to s raised to df. So we can say it is the line only, and it is look like a 2D object if we are folding that curve. So this is all about the Hilbert curve. So we have to remember that the Hilbert curve is having the topological dimension as a 1, and the df, that is nothing but fractal dimension, as a 2. This is very important while we are drawing the curve. Then next is triadic Koch curve. The question can be on this like you have to explain the Koch curve, or what are the different fractals. If the question is like what are the different fractals, so in that you can mention the Hilbert curve also and the Koch curve also. So this is again a very important question, and we have to cover this in our practical assignment. So now we'll see what is the Koch curve. Why its name is triadic Koch curve, we are going to see now. To draw this Koch curve, we have to start with a line segment. Again, it is starting with a line segment. Then we are dividing that line segment into the 3 equal parts. So what we are going to do, we are dividing that line segment into 3 equal parts. Then we replace that central part third part by the two adjacent line, means whatever the parts we have done, from that the central part is replaced with the two adjacent sides of the equilateral triangle. Equilateral triangle means triangle having all of its three sides as a equal. So we are going to replace the one side of that equilateral triangle by the another two side, and then we will get the neve length of that curve as a 4/3, and again we are doing that repeatedly to form the fractals. So how it will look like, we'll see. Now here we can see that this is what your original line segment, then we are dividing that line segment into the three equal parts. Okay, so in this second thing we are dividing the line into the three equal parts. Then what we are going to do, after that we are replacing the central third part of the of that line segment. Central part of that line segment is nothing but this part. We are replacing that part by the equilateral two sides of equilateral triangle. So whenever we are considering this line with the equilateral triangle, so we are just replacing this part with the another sides of equilateral triangle. So now you can see that we have divided the line into the three equal parts, then middle parts is again replaced by the equal parts of equilateral triangle. So this line is having now four parts, and all the parts are of the same length. You can see here the line is replaced with the four different parts of a line, and all parts are same. So what is the big thing is here, that your starting point and ending point is not changing, as it is changing in Hilbert curve. Here the starting point and ending point is not changing, they will be same, only the middle part of that line segment is going to be changed for every iteration. So we can say that here the curve whose end coordinates are same as that of the original segment, but it is built of the four equal length segment. So starting ending point are same, only it is changing with the four equal length segment. So each of this length segment is having the size of 1/3. So the new length of the curve will be 4/3. So whenever we are considering this curve, and if I want to achieve again my original object, that is nothing but line segment, so how many parts are required to draw this original object? Obviously these four line segments. These four line segments are required to draw the original length segment. So in this you can say this is the first approximation. Whenever you are replacing the middle part of that line segment by the two sides of equilateral triangle. In the next approximation, what you can do, again this is what the one line segment, this is what the one line segment. You can divide this one line segment like this again into the four segments, right? Then again next is, this is the one line segment, you can divide this line into this four segments. Again this is what the one line segment, you can divide this line segment into the four segments. Again this is what the line segment, you can divide this line segment like this. So this is what the next approximation of this line segment. Again in that case you can see here the starting point and ending point are the same, only the middle curves are changing over here. So for the second approximation the curve will look like this. Again you can consider as this is as a single line segment, and again you can divide this into the four part. Same way you can divide this line, this line, this line. So this will be again a continuous process, and it will go again infinitely long. So we can say here that the length of this Koch curve identically is nothing but infinite. This curve doesn't fill the whole area like the Hilbert curve. Hilbert curve is filling all the squares. Here the Koch curve is not filling the all square. Why its name is triadic? Because it makes the triangle like with this three segments. That's why it is called as a triadic Koch curve. Now it does not deviate much from its original shape, means it maintains its original shape, not much divert from its original shape like a Hilbert curve. We can say here that it is reducing its scale by 1/3, because what we are doing initially, we are dividing the line segment into the three parts. Means what we are going to do, we are making the scaling factor 1/s is equal to 1/3. Therefore value of s is what? 3 here. So we are scaling that factor with the value 3, and we can find that whenever we want to the curve that is look like our original one, means this is the line segment, then what we have to do, we have to join all these 3 different parts, right? Not 3 but this 4 different parts, because we are replacing the middle part with this sides of equilateral triangle. So if we are combining these 4 parts, then we will get our original line segment. So the value of n is nothing but 4. It requires the 4 different parts to join the new original object, and the scaling factor, that is s, is having the value 3 because it is dividing the line into the 3 parts initially. So we know that n is equal to s raised to df. So n is having value 4 and 3 is nothing but scaling factor s is equal to 3, then we can find df. So we know that the formula of df is what? df is nothing but log n divided by the log s. So log n divided by log s. So n is having value 4, s is having value 3. So df is nothing but 1.26. Again we can say that the topological dimension of this triadic Koch curve is 1 because it is made up of line segment, and we know that whenever we are considering the line segment, then dt is 1. Whenever we are considering the plane, that is x and y coordinate, in that case dt is 2, and whenever we are considering the 3D object, then dt is 3. So here we are considering the line segment, that's why the dt is nothing but 1. That's why the topological dimension is 1, and whatever we have found out, that is nothing but the fractional dimension, that is equal to 1.26. So here we can say that the fractal dimension is greater than the your topological dimension, and whenever this case happens where your fractional dimension is greater than topological dimension, that time you can say that curve is nothing but a fractal. So before that we have seen the Bezier curve and B-spline curve. They are not having their dimension, that is fractal dimension greater than topological dimension. That's why they are called as a curve. Here the fractal dimension are greater than topological dimension. Therefore, these curves are called as a fractals. So curve whose fractal dimension is greater than its topological dimension, then it is called as a fractals. So Hilbert curve and Koch curve both are a fractals because they are having their df, that is nothing but the fractal dimension greater than dt, that is topological dimension. So here 1.26 is greater than 1, therefore this Koch curve is also the fractal, and here you can see that the df, that is value 2, is greater than dt, that is 1. 2 is greater than 1, therefore this Hilbert curve is also called as a fractal. So question can be like, why the Hilbert curve and this Koch curve is called as a fractals? So for that you have to prove that their the fractal dimensions are greater than topological dimension. How? You can use the formula to show that how it is greater than its topological dimension. So this is all about your fractals. These are the two types, triadic Koch curve and Hilbert curve, which are nothing but fractal, and we have to see both this curve generation in our practical assignment. So we will see it soon. Thank you.